So the answer to that question, what may be the better way of studying the Higgs boson, is not collide these complicated objects called protons, but collide something which don't have any internal structures. They are real elementary particles. And we know such a particle which we just talked about, namely electrons. But colliding electrons on electrons don't produce very much because you can't convert energy efficiently to something else. So you'd rather collide electrons against their antimatter particles. And we will talk more about this in the third lecture. So if you're bringing electrons and positrons, that are the antiparticles of electrons, you smash them against each other, then because they're elementary, what you see is actually fairly simple to understand without having this complicated mess we've been talking about. But in order to build such a machine, it's actually super high tech. You accelerate the beam over, again, 10 miles or so, or 15 kilometers or so. You focus the beam down to an incredibly small size. That beam itself, this collection of electrons, is as small as a few nanometers, like tens of atoms. The fact that you can focus beam so small is really an incredible technology. But another incredible part of this technology is that you can make sure that these small things actually meet each other. And the claim by our accelerator builder friends is that you can actually do so. And if you manage to build such an experiment, we can study the properties of this new particle in a greater detail than LHC can do. So here's sort of a picture of this. When you're colliding two protons against each other, then what you're looking for is actually the collision of the small pieces inside, like quarks. So that's what you're looking for. But the rest of the things inside proton just keep flying, and that creates a complicated mess. On the other hand, if you're colliding electron and positron, they are the point-like objects, and they annihilate into energy that gets converted to mass of new particles, again, E equals mc squared. You can use its full energy without this additional mess. And you can also produce all particles in rather democratic fashion, and you can also capture a complete information because you don't have anything sort of running down the line. So I use this analogy. Is the proton is like a cherry pie. And you're colliding cherry pies on cherry pies, which is a fairly easy thing to do if you think about it. But what you're really after are the cherry pits inside the pie hitting each other. And inside this complicated goo of things flying apart, it's very difficult to spot that. But the idea of colliding electron and positron is like throwing cherry pits against cherry pits. And of course, technologically, that's more difficult to do because you have to make sure the pits meet against each other. But if you manage to do that, you really see the simple collision of these cherry pits. That will be a much more clearer way of studying the nature of these new particles. Well, LHC will keep running for another 20 years or so, and we're looking forward to even better data coming out from the LHC. But the discussion to build this new kind of machine has just started. And the person who actually built the LHC, Lynn Evans, visited Japan recently and actually ended up meeting with the Prime Minister Shinzo Abe. And he wanted to convey the idea that all the people in Europe are looking forward to the contribution of Japan in this next big machine. I was there also as a translator next to him. Anyway, I don't know if this would happen, but that would be a very interesting way to study the very beginning of the universe. Namely that we talked about this fusion of helium out of protons, neutrons, when the universe was only 3 minutes old. This already sounds like a very young, hot, small universe, but we would like to go further. Studying of the Higgs boson is going to tell us how the universe was like when it was 1 quadrillion degrees temperature, and that was when the universe was only a trillionth of second old. So this is the way we wish to approach further back in time towards the Big Bang itself. So this kind of journey not only addresses the question where we came from, but at the same time addresses the question, how did the universe begin? And we may have a chance of making even more progress. So when the Higgs boson was discovered, all newspapers reported this following question. We used to know 16 types of particles. 17th particle is the Higgs boson, and that was meant to complete the story. Well, 17 sounds like a weird number, doesn't it? So how come that there are 17 individual particle species in nature. And talking about these 16 particles is sort of a simple way of doing so, looking at this table. But if you look a little bit more closely, you can actually count 45 different kinds of states among these particles, it turns out. And that's only for the matter version. Antimatter version adds another 45. So there are actually quite a large number of particle species inside this table. So that is a little strange, isn't it? We're talking about the elementary particles. They are the fundamental building blocks of nature. Why do we need so many of them? We don't have a good answer to this question yet. But maybe there is a better theory out there, which we haven't really found yet, which unifies all these different particles into one matter particle. Maybe all kinds of forces we see today into a single force. And that kind of idea is still a dream at this stage, but it's called unified theories. After all, we have seen a good example of unified theory before. These 100 of elements we see on a periodic table could be understood in terms of this single picture of electrons moving about in atomic nucleus made up of protons and neutrons. So only 3 objects, electron, proton, neutron, allowed us to understand all these 100 chemical elements. That is one big unified description, isn't it? It turns out that such a theory might exist, called grand unified theory. If you go to very back to the beginning of the universe, it was so hot, the forces behaved with different strength. So what we see today, we already mentioned 3 kinds of different forces: electromagnetism, weak force, and strong force. They have rather different strength as we measure today in our experiments. But maybe early on, the beginning of the universe, they had exactly the same strength. They were of the same strength, a single force. And that kind of possibility is at least possible theoretically if you find yet another kinds of particles called superparticles. And if this is the right understanding, we don't know yet, but we keep looking. So that's the idea, is that our nature not only has 3 dimensions of space, there could be even extra dimensions, but even something called quantum dimension to it. And if a particle has its antimatter version, for electron, there's a positron. But if these particles wander into these strange quantum dimensions, they come back at yet another form of superpartners. And this has to also do with the nature of dark matter, as we discussed in the next lecture. So, especially in physics, we are always looking forward to next layer of unification. We talked about Newton. He unified our understanding between how apple falls from a tree and how planets revolve around the sun. And that's an incredible unification. These very different things are very different distance scales. Something you can touch, something that's in the heavens. They follow the same laws of physics. And that was one fantastic example of the history of unification in physics. And out came this F equal ma, laws of mechanics, and the inverse square law of gravity. Electric and magnetic forces had also been unified by a physicist named James Maxwell towards the end of the 19th century. Now we speak of electromagnetism, not electricity and magnetism as something independent. There was yet another form of unification, and this actually led to the invention of radio communication and many other useful other consequences. At the time of the Einstein, that there had been several phenomena that came from study of atoms, and that eventually led to something called quantum mechanics. And there were other phenomena that led to the discovery of electromagnetism, weak force, and strong force. So this was sort of the scattered things which nobody had a very good unified understanding of. Einstein actually tried to bring in electromagnetism and mechanics together in his theory called special relativity. And as we talked about in the first lecture, he went further and put that together with Newton's gravity and explained why objects of different masses fall the same way. That was the theory of general relativity. So you see there's a line of unification going on that way. Now what about this side? Well, it turns out that there was indeed further unification going on. The electromagnetism, relativity, quantum mechanics, and some decays of the nuclei got unified into this single theory called quantum electrodynamics. And now, together with this Higgs boson, which is a study of the weak force, we're witnessing, hopefully, another layer of unification. This quantum electrodynamics and the weak force gets unified in something called electroweak theory. And that's still emerging. The study of the Higgs boson is the beginning of that. And beyond that, only a speculation. But as you saw on the previous slide, maybe we can combine this electroweak theory together with a strong force to reach this grand unified theory. And if you further put that together with the general relativity theory of gravity, we might find something called string theory. And that's beyond the scope of the class I'm teaching right now. But you might look around and find a lot of interesting information about this grand unified theory and string theory on the internet. And if you manage to build this new type of machine, let's say you have this extra dimensional space, then you have this big collision of particles, and sometimes particle might fall into the extra dimensions, and it looks like you have missed something. And that will allow us to actually even measure the number of these extra dimensions and their shapes in doing experiments. And having found these extra particles you might have predicted in this theory of supersymmetry, and that would allow us to test this idea of also grand unified theory by trying to see if the masses of these particles become the same at the beginning of the universe. So I'm only touching upon these subjects, and I hope you will look up on many other subjects and topics in the other places. But hope is that by doing a next generation of experiments, not only we might see how the universe was like when it was only a trillionth of second old, but even we may be able to approach the Big Bang itself, an incredible high temperature and an incredible short lifetime of the Big Bang. So we don't know if we get there, but again, that's the nature of science. We just keep trying to understand and approach as much as possible we can get to the very beginning of the Big Bang. So the next lecture is about dark matter and antimatter. We briefly touched upon both of them so far, but we look at them in more detail and ask the question where they came from, why that is important for us, and what should still be done for us to understand the nature of these interesting subjects in physics.